This lecture focuses on practical application of Fourier analysis to real signals. So there's lots and lots of uses of trying to understand the spectrum of signals and in communications and mechanical systems, trying to find out where the oscillations are, and natural phenomena like ice ages or tides or sunspots. One of the things we've mentioned before, but now we're going to focus on is the effect of windowing. Remember, windowing is what happens when we have a finite, limited observation time, and for kind of a schematic way to view it is that we have some real signal and we have a switch where we turn on. This could be a recorder or an analog to digital converter, and the output is what we call XW of t. And the math model, and we've talked about this a little bit before, the math model is it's as if we have the original signal and we view it through a window function, and I'm going to call that W of t. Now let's work through a little simple example for a real simple case, but this is an important case where x of t is a sinusoid. Okay, so this is a real important case because many times we're trying to identify the presence of sinusoids in a signal, and sometimes there's a lot of noise and we just want to find out if it's there and what its frequency is. This is a periodic signal, so it has a Fourier series. We also, as I mentioned before, we also can come up with a continuous time Fourier transform if we allow delta functions to exist. So this has a continuous time Fourier transform that's made up of a delta function at f naught and another delta function at minus f naught, which we represent as f plus f naught. Okay, to kind of picture what's going on, so I'm with this whole idea, we're going to picture turning this on and then turning it off. I'm going to draw two pictures, a time domain and a frequency domain. Okay, time on the left, frequency on the right. Alright, so let me draw the sinusoid, if I can draw it here. So this is going to be x of t, and it's just a everlasting, never-ending sinusoid. And I won't try to be real careful about drawing it. Everybody knows what a cosine wave looks like. And we're going to model the switch effect by this window function, and I'm going to assume that we're going to turn the switch on here and we're going to turn the switch off there, and just to make it a little easier to understand the math, we're going to make it symmetric and makes the math a little easier. Minus t over 2 is when I'm going to turn it on, and when t is equal to t over 2 I'm going to turn it off. So that's the time axis. And within that range, when the switch is on, it doesn't amplify or attenuate the signal. It just has a gain of 1. So I'm going to multiply x of t times w of t. This doesn't multiply. And the final result is the windowed signal. And I'm going to draw it with red, and it's going to look like this. It's going to be 0 until we turn the switch on, and then it's going to be a sinusoid. So this is the part we observed, and then it's going to go back to 0 when we turn the switch off. So this is the windowed function that we actually observe. Okay, we don't observe any of this stuff before and after the switch goes on and off. What about in the frequency domain? The Fourier transform of the sinusoid is two delta functions. Let's put them right there and right there. They have a weight of 1/2 minus F naught plus F naught. So this one here is that one there. This one there is a delta function shifted to the right out to F naught. So this is our x of f. So Fourier transform of a sinusoid, all its energy is at these delta functions exactly at F naught and minus F naught. Alright, multiplication in time domain is convolution in the frequency domain. One of those fundamental ideas that we've talked about that you really have to know. What's the Fourier transform of this rectangle? You should also really know that a rectangle transforms into a sinc function. Let's see if I can draw a sinc function. I'm not going to try to draw it very carefully, but it looks like that. So this is our window function, Fourier transform, x of f. Pardon me, that's w of f. And it's equal to T sinc Tf. Okay, so that's the sinc function. That's a function of frequency. Alright, now usually convolution can cause us troubles, but now we're convolving this sinc function against a couple of delta functions. And I hope you also remember that when you convolve things with a delta function, it's just going to make a copy of this to that location and to that location. So we're going to have a sinc function at F naught and at minus F naught. So this is the spectrum that we actually observe when we do the Fourier analysis. Remember, there's no way we can observe this thing. It's never ending. It lasts for an infinity of time. So if we had godlike properties, we might be able to observe this. And this is the spectrum we'd see. But being mere mortals, we have a finite observation time, and we see a spectrum that looks like this. Clearly, this signal is different than that signal, so this spectrum is different than this spectrum. And what we'd like to do is try to analyze what we do observe and try to work out what the original signal is. So we might be able to infer that there's a spectral line at F naught and minus F naught, and infer that there's a sinusoid in the data that we're looking at cosine F naught, for example.